For that. So my name is Alan Hasse. I'm a vice president here at Avaya. And, there's a lot of fascinating things happening at both edges of the network, right? So in the data center, as Randy and Paul talked about, you have virtualization of compute, storage, applications, and the network. At the other end of the network, there's a number of phenomena that are affecting what's happening to the network as well, and the campus is kind of the thing that ties it together. And so, as Paul described, we're really leveraging our fabric technology that we've taken from the data center all the way to the edge of the network, both wired and wireless. I'm going to talk a little bit about why we're doing that and kind of the phenomena that are actually driving us to do that. So let me start kind of from the outside in and just work through, what's affecting the network from the edge in. The first is BYOD, and the BYO isn't really the most important part here. It's really devices. And it's devices on a couple of different levels here. First, the number of devices that we carry. No longer are we just lugging around one. I'm guessing most of you have 2, 3, anybody 4, 5 devices? 5, okay, so number of power users here, right? Rewind 5 years ago, probably only carrying 1, maybe 2. So the number of devices, 4, okay, so number of devices increasing quite a bit, which is, creating a set of demands on, how we manage all these devices coming into the network, what services they get, what applications they get, how do they get mapped back to this data center piece. The third phenomena is the types of things that our devices doing for us. So our devices are getting much smarter on our behalf. And as Paul mentioned, we did the Sochi Olympics, and we learned a number of things about the Sochi Olympics. One of them is, so what applications do people actually use at these types of events? And so during the closing ceremony, the 2 top applications in terms of consuming bandwidth during the closing ceremonies were Dropbox and iCloud. Now, most people, when I talk about this, would quickly guess FaceTime, Instagram, the Russian version of Instagram, Twitter, things like that. But ultimately, our devices are doing things on our behalf. So people are taking pictures, right? Natural thing to do during the closing ceremonies or at any big sporting event or event of some kind. And our devices are then taking those pictures, uploading them. It's an Android device, Dropbox, or even cameras now. Many of them have Wi-Fi interfaces. They're going to Dropbox. iPhones go to iCloud. And similarly, as we're sitting here today, our phones are probably downloading email, updating Facebook, probably multiple email accounts, right? A personal one, a professional one, potentially others. So a lot of stuff going on in the background. It's really important to not only understand what's going on with those devices, but what they're actually doing on our behalf, and then how that affects the campus network and how you need to connect that to the data center. So the second thing that's really happening at the edge of the network is the move to 802.11ac. This is largely being driven by a number of things. Number of devices is going up. So the more devices you have, the more just background bandwidth that they consume, whether they're doing things like updating Facebook or email, or just keep alives and things like that consume a lot of bandwidth. So we need to get to higher speed wireless. And then it's also true that wireless is becoming primary access and mission critical to almost all the customers we talk to now, whether it's education or state and local government or healthcare or financials or big enterprises or even mid-market customers. So many of these devices that we're bringing in don't even have Ethernet ports anymore. So they need high bandwidth wireless, and they need it to work incredibly reliably to be able to do that. And then finally, they actually need, and there's, if you look at many analysts, they're talking about unified access because people want to be able to get access to the network however they choose to, wherever they're at, and have a common set of policies. And so Randy talked a little bit about a policy engine, but really it is policies that start to bridge what users want to do in terms of the devices they bring, the applications they want to run, as well as how they connect. And it bridges them to what IT staffs actually want to enable them to do, right? So I think if you'd ask most IT administrators, they just as well ban BYOD, only have corporate issued devices that only run certain applications, but that's just not the reality that they live in anymore, right? Whether they're being driven to or they desire to embrace these things, they need to have a policy to bring some sort of order to bridge what users want to do and what they actually need from a security perspective. So, and that kind of spans wired or wireless. So what we've essentially done is, you take the same technology SPB and you start to bridge it to, first the wiring closet switches, for so that you can actually take all of these devices in the end speak, VLANs on this side and start to map those VLANs into ISIDs. So you can start to, map into layer 2 VSNs, and then, in your core set of boxes here, you can map them to, layer 2 or layer 3 virtual networks, VRFs if you have it. And you want to be able to do that in an automated way, right? So
just for clarity here, you didn't extend the shortest path bridging cloud. Now we've got 2 different SPP clouds that are bridged across a core with more traditional protocols. Is that?
It's actually SPB all the way from the data center onto the edge switches.
So it is a single unified fabric.
Which brings me to an interesting question. What's the maximum number of nodes that you would support in an SPB domain?
So today we do, and there's a couple of different ways to look at it. One is 250 nodes, so 250 wiring closets or stack. Each stack counts as a node. We're scaling that up to roughly 500 over time. You also have to think about how you segment this up just in terms of normal things with ISIS and, bandwidth, things like that.
Number of routers in ISIS domain, 250 today.
No. So it's always a box problem, right? So even with those OSPF or BGP, it's really about the smallest box you have.
Yeah, I know.
So
that's why I'm asking.
Yeah, so in certain boxes itself, they can have 250. We have networks deployed that are near 1,000 nodes.
Okay.
So it's a combination of which boxes and how you design.
And it's a single ISIS area.
Single ISIS area, yeah. Moore's law has been phenomenally kind in that perspective. Yeah.
Exactly. So we run SPB all the way out to the wiring closet. We introduced this last year. This provides a number of benefits to customers. As Randy mentioned, we have a policy engine. It's actually called Identity Engines. And this is kind of our core policy database. So it allows administrators to say, this is Alan accessing the network and he's using a corporate device or his own personal iPhone or Android device or tablet or what have you. And then it tells, based on the policy, the administrator may say, okay, Alan's an employee, he fits into this group for personal devices ends up on this VLAN mapped to this ISID, and Identity Engines tells the switch, hey, on the access port that Alan just plugged into, whether I'm in my office or in a conference room or somebody else's office, I want you to add this VLAN to that access port, and I want you to map that VLAN into this ISID on the uplink. So if the ISID doesn't exist on the uplink, it tells it, hey, I want to be part of this ISID, this layer 2 VSN now, and then that propagates back through the network so you never have to touch the core in order to do this. So
how do you profile the client?
So we do it in a number of ways. We use 802.1x. We can actually actively profile the device and understand as it's authenticating what type of device it is, whether it's they're pretty straightforward in terms of how they look at DHCP requests and all sorts of things to know what type of device it is. So,
but it is agentless then.
It is agentless, yes. We don't rely on anything to be on any of these devices. That's extremely complex. Exactly, profiling traffic and making some assumptions about what it is and then mapping them into a group, right?
So you just described that basically to a wired port. What happens if you extend it one more time and you put an AP that has SSIDs, etc.? So
this is essentially what we delivered late last year. What we're delivering today and actually announced yesterday is you have a wireless LAN access point, say an 802.11ac access point over here. And we've used our fabric attach technology to be able to extend the fabric from an edge switch all the way to wireless LAN. The way this works is, let me just start from a very basic scenario. You plug in an AP, the switch recognizes it, the policy engine recognizes it and says, hey, this AP needs to talk to this management station. Actually I'll draw it over here. There's some management station that sits back here in the data center. And that happens over, let's just say it talks over some VLAN, 11 or something like that. So it'll tell the edge switch, map VLAN 11 onto this port, and VLAN 11 maps to this ISID, and now you have connectivity to the management station. Once it contacts management station says, hey, I want you to broadcast 2 SSIDs, employee and guest. An employee has WPA2 and what have you, and guest, let's just say, is wide open. Or points you back to a guest portal out of Identity Engines.
You have to touch to provision that AP somehow to let it know that it wants to do that?
Nope. So the AP, it understands what its default VLAN is. Let's say it's 11, and the switch detects it and it connects it.
It said it understands.
The AP.
How does the AP know that it?
Oh, by default.
APs don't have a default.
No. So these are our access points, right? So they. At the factory, exactly. Right. So anyway, so you get connectivity to the management station. The management station now tells it, broadcast these two SSIDs. These two SSIDs map to, let's say, VLAN 12 and 13. The AP actually tells the switch, hey, I want to be part of VLANs 12 and 13, so create those on this port. And the switch will then map these to the right ISIDs on the uplinks as well if they don't already exist. Now you have, any of these types of clients talking over, 2, 4, or 5 gigahertz, whatever your wireless policy is, onto your AP. Now the beautiful thing about our fabric is, as you've noticed, we actually do not have a controller in this particular diagram. So as we started to look at what was happening in the enterprise, especially as people moved to primary access 802.11ac, controllers solved a big problem early on. One was management and scale, but the real issue was mobility and roaming, right? It's because the underlying network didn't really deal with roaming and mobility very well. Our fabric actually, because of what it does in the data center, helps deal with that in a significantly better fashion, right? So we can put these essentially SSIDs to VLANs, VLANs to ISIDs, group all the APs into, say, a large VSN, and now all of your APs and all of your roaming data is all contained within that VSN, and so that clients can roam over here. Your traffic is just handled by the switch. No longer you have to hairpin traffic or tunnel traffic all the way back through some centralized controller. You just let switching be switching. This has a number of benefits. I think anybody that's familiar with wireless and controllers, multicast is a problem, broadcast is a problem, right? None of these things scale. Multicast is hard no matter what, right? Multicast, it is, right? It's just hard, right? So
One is using it apart from a few people.
So if you had two APs over on the edge, when the client roams, I understand the client basically stays in the same VLAN the entire time. That's great.
Yep.
But how does his authentication?
So essentially, the APs, share through the fabric. Hey, I know about this. I know about this client. Here's how it attached to me, and so as you roam, it essentially does exactly what it does on a controller. Just does fast roaming.
But the controller knows where all the clients are. You don't have a controller.
So what we've done is we've taken the two pieces of the controller. There's a management control plane piece. Put it in the management piece. Put the data plane piece in the AP. So the control plane piece of it is in the management. So control plane is here, and so it's a distributed control.
No, it's a controller the way controller should be understood.
It's not a box that says hi, I'm a controller.
It's not controller.
There's not a centralized controller here. Right?
No, it's controller. The way
Yeah, there is a controller.
But
Yeah.
let's just
for the
make it
regular
very
definition of
simple.
controller.
Yeah,
One client's attached to the AP.
Yep.
He does his 802.1x authentication.
Yep.
He has a key that needs to get pushed to the next AP,
Yep.
who's one hop neighbor away.
Yep.
Who sends that one hop neighbor key to the next hop?
APs share this information between them.
So there's another protocol, AP to AP protocol.
Yeah, it just uses IP. So it just essentially relies on IP connectivity between them.
Plane is in both places.
Yeah, I mean that's
That's probably a proprietary protocol.
and that's
Yeah,
really
it's
my
still a
question.
control
plane.
So you do have
Could
a
be
control
proprietary.
plane
Exactly.
protocol
Right.
that's proprietary.
Exactly.
It's AP to AP.
Yep.
Yeah.
Yep.
And
It's
same
control
with
plane,
with radio research management. How are you handling?
Same thing, right? So we share information between the APs so that they can make intelligent RF decisions between, I want to broadcast this channel, this power. Exactly. Yeah. And as you see, a number of architectures that are starting to emerge from vendors that are looking at 11AC are being more of this hardware controllerless type of architecture to essentially deal with the performance, right? Hairpinning all the. There's really, the need for a controller to deal with mobility and deal with sharing of keys and all of that was important. But bringing all the traffic, especially if you're thinking about a gigabit per AP.
Data plane's obvious needs to
Yeah, right. So it just needs to be.
I was just worried. How do you do the control plane
Exactly.
issues? And you kind of which control planes are back at the management?
So it's mostly policy type things. So and reporting and troubleshooting. So
But that typically, most wireless vendors that I've experienced with don't call that control, they call it management. That's,
yeah.
so, am I right? I'm not the
No,
expert.
Yeah,
but-
in wireless you call the data plane tunneling controller.
Exactly.
Yeah, that my confusion. I was agreeing with her.
Okay.
When you
Yeah,
say
I'm-
control back at the management,
Yeah.
Yeah,
management's still management. Control is now in a
Thank
Thank
protocol.
you,
Exactly.
thank you.
Yeah.
but the management
I'm
can
more
live different
Aerohive
places
and
as well.
Airtight, so that's.
So AeroHive kind of does a similar thing, right? They have a Hive and a controller that's kind of built into their AP, right? So Yeah, so it's an architecture closer to that than what, say, a Cisco or Aruba is with a centralized controller, although Aruba has Aruba Instant, right? So it's sort of similar type architecture. So the other thing that we've done with wireless, because all these devices, if you recall back to my Olympics example of Dropbox and iCloud, we actually see the need, and again, being an application company, the need to do application QoS inside the AP. So we build a deep packet inspection engine inside the AP that can recognize up to, over 1,000 different types of applications. So one, people can actually start to discover what are people doing over their network, right? I hear from CIOs all the time that, hey, I'm being asked to go 10 gig out of the wiring closet to the core, or 40 gig out of the core to the data center. And I take that to my CIO and I say, hey, I need more money to go do this. And he goes, what possibly are people doing? I sit in my office and I do email. Like, how do we need 10 gig uplinks here, right? So giving them the visibility and the data to actually go, one, understand what it is, and two, be able to deal with it, right? So maybe I'm an educational institution and I want to block Dropbox and iCloud, or I want to block, upgrading iOS over my wireless infrastructure. Maybe I want to do that for a time of day.
You're not doing intercept, so you're like basing it on flows.
So, exactly. So we have a deep packet inspection. So we're actually, inspecting the.
Not if you're not doing SSL intercept and it's encrypted.
So if it's encrypted, no. Then ultimately what we can see is, okay, it's an SSL tunnel or it's an IPsec tunnel or something like that. But many applications aren't, right? The other thing that tends to happen if you look at many of these applications is, just like in the data center, there's a lot of kind of east-west things going on. Many new applications that our devices do are east-west as well, right? So traditional mechanisms of putting a URL filter or something at the WAN edge and trying to block traffic here don't work for things like BitTorrent or even, iMessage face. What? Tor, exactly, right? Because they're all going point to point, right? So again, administrators want to be able to know that and go, okay, I want to, either want to monitor it, I want to block it, I want to rate limit it, I want to prioritize something else to ensure that everyone gets the best.
I mean, like you say, you have 1,000 types of applications, but without SSL intercept, you really don't, because there's a lot that's encrypted that you just.
There is, but there are many that aren't, right? So you can,
And there are some that aren't obscured as much. You can probably tell pretty easily if something's trying to send something to Dropbox, even if it's over
whether
SSL.
it's encrypted or not, right? I don't care what's inside.
But you're doing that based on usually not like application profiling. How are you doing that then?
So we're looking at, some of these things can be looking at, the URLs and what they're going to, right? So we don't care what's in it. Yeah, just like BitTorrent. I don't care if it's encrypted. I don't care what they're doing with BitTorrent. I just care that they're doing something with BitTorrent.
DNS ports, things like that.
Apply
Yeah,
this
do that.
application awareness and QoS back to all the wired clients as well?
So we have a separate technology. I'm going to wrap up with this because we're almost out of time. That we've actually baked into all of our switches, our access switches and our core switches. Not necessarily application recognition, because many of these things are hardware, off-the-shelf chipsets. But it actually starts to measure latency, jitter, and delay and packet loss, behind the scenes between different subnet switches, infrastructure, things like that. And we have another server back here called the Avaya Diagnostic Server that collects all that, and it can actually start to provide data to IT administrators to give them, hey, if I'm a user and I complain that voice quality was bad, or I get call drops, or my video conferencing system was very poor last Tuesday, they can actually go back and look in time and see what the infrastructure was seeing, not just net flow, but actual live inspection of what latency, jitter, delay, packet loss actually looks like. So largely around new 11AC APs, this application QoS component, and improved network management, all tied in with Fabric attach into our end-to-end Fabric.
So effectively, you're using the same Fabric attach on the wireless access points to connect to the switches.
Exactly.
Okay.
Summarize everything I said in 10 seconds. Excellent.
You just thin slice it.
Excellent. Well, thank you all very much for your time. We appreciate it today.
Thank you.
Thank you.